I'll just get started. First, I'd like to thank Zhang and Christine for organizing this and the invitation here. I think I know some of you, I don't know all of you, and just let me give you some information about the research I'm currently working on. So I'm doing a lot of work. My work basically is to integrate laboratory studies, field studies, and modeling studies to understand the impact of atmospheric aerosols in human health, weather, and climate. So I'm going to talk today about nucleation growth of aerosols based on field measurement and some laboratory studies. I also do some work concerning combustion. Recently, I'm working with my colleagues on shock tube to generate soot particles, understand aging of soot particles under laboratory conditions, ambient conditions. In addition, also do some modeling work, understand the impact of aerosols on cloud formation and climate. Okay, so Rick gave a very good introduction, so I don't have to talk this too much. So basically, when you look into atmospheric aerosols, there are some very critically important properties that determine all the impact of atmospheric aerosols, such as the number concentrations, the size of those aerosols, the chemical compositions, the hygroscopicity, optical properties, and etc. And here I'm going to talk about some of those mainly relevant to particle size, number and size, and chemical compositions. And this is an article which is recently written up for Chemical Review, the thematic issue on climate, on formation of urban particulate matters. So essentially, if you look into the number concentration of aerosols, there are two origins. So one is primary emission. You can have soot particles emitted into the atmosphere by combustion process, dust, and etc. Alternatively, you can also have gaseous molecules that undergo oxidation reactions in the atmosphere, and eventually they form molecular clusters, and they engage in nucleation and then lead to aerosol nucleation process. And of course, both primary particles and new particles will undergo aging process or growth process, and eventually give you those particulate matters. So what I'm going to do here right now is to present some data, some measurements that we've been working on under clean conditions, very polluted conditions, and to understand the nucleation and growth processes. And also I like to address some of the challenging issues in terms of understanding aerosol nucleation and growth. So here are some measurements we did in Houston, Texas. And showing on the top is the average particle size, the average particle number. And the bottom here are the optical properties, the single scattering albedos. So one thing I do like to emphasize here is that we have been doing measurement in a lot of locations: Houston, Mexico City, California, Mexico borders. In most of those places, we see very, very clear diurnal patterns. So basically, if you measure the particle size, you see in the morning hours, they start to grow a little bit, and then the size may actually shrink a little bit. And if you look into the the particle number concentration, the highest occurs at night. And also, if you look into the optical properties, because primary emission soot particles, you see a very high absorption and very small SSA. So this kind of diurnal profile is very well understood in terms of the emission sources, the photochemical processes, and also the loss processes, particularly the variation in the atmospheric planetary boundary layer. And one thing I do like to mention is that in Houston, it's polluted, but it's not that really polluted. The NOx concentration is not that high, and VOC concentrations are not very high, and therefore you don't actually see very efficient growth processes. However, if we do the similar measurements in some very polluted environment, and those are measurements we did in Beijing. This is 2000 September to November in Beijing. And the top one here is a mass PM5 mass concentration, PM2.5 mass concentration. And the second column here is a the the size distribution, the particle size as a function of time, and also the contours here is the particle number concentration. And based on the size, we can calculate the average, the size distribution, we can calculate the average particle size. And the bottom one here is the average particle number concentration. So what you can see here is that in Beijing, so all the PM properties exhibit a cycle, but this cycle is not diurnal cycle. And you see this concentration rise sharply, but then come down to very clean conditions. And the cycle here normally is 4 to 7 days. So in a very polluted place like Beijing, they actually lost a diurnal pattern somehow. And the other thing I do like to mention, Rick mentioned about aerosol nucleation. So we do see that each of the pollution episode, there's an aerosol nucleation. And also you can see that throughout the course of the haze accumulation, there's a gradual increase in the particle size. And also in the case of Beijing, because the very efficient aerosol nucleation, you can see very high concentration of particles. So, and I just like to give you a little bit more detail regarding the haze development in Beijing. So this is one episode, and in September 25th to 29, and this is another case. Again, so this is number concentration, and you superimpose here is the average particle size. And again, this is a PM 2.5 concentration, and those are the chemical compositions measured by aerosol, the aerosol mass spectrometer. So what you can see here is that each of the pollution episode consists a clean period and transition period, and very, very polluted period when the PM 2.5 reaches several hundred microgram per cubic meter. But throughout the 3 periods, you can see in the beginning of the episode, you see very clean signature of aerosol nucleation. So aerosol nucleation is a big factor in Beijing, so it's nucleated very efficiently. And also you can see the particle also grow very efficiently throughout the course. Let me just give you one example here on this particular day. So on 27, 28, initially the PM 2.5 was below 50 microgram per cubic meter around in the morning. So the visibility was very good. But by the end of the day, the PM 2.5 rose all the way to 300 microgram per cubic meter. And of course, you can see those organics as compound really play a big role here. So what I want to emphasize here is that in Beijing, there are 2 very distinct processes responsible for the haze formations. One is a very efficient aerosol nucleation, and they basically set up the stages. So once the conditions are right, the particles grow rapidly that create the extreme hazy conditions, and you can see that are the other cases. So the pollution case in Beijing is characterized by very efficient aerosol nucleation and very efficient growth process. A little bit more about chemical composition here. So I plotted here are the 2 episodes. So we have clean transition, polluted period, and those are how the chemical composition evolves during those 2 polluted episodes. So you see in the beginning, most of those organics, and but as the haze event develop, you see more increase in concentration, mass concentration of inorganic species, primarily sulfate, ammonia, and nitrogen compounds. And the other thing we have done some other measurement. Rick also mentioned this. So we also measure some other aerosol properties such as hygroscopicity and also density of those particles, which also provide some additional information regarding the chemical constituents of those aerosols. So the dashed line here is hygroscopicity again. So this is one episode clean to polluted case. You see, initially, because aerosols are mainly organic aerosols, they are not very hygroscopic, but when they grow and they really become fairly hygroscopic, and you also see some soot mode here, soot which is not very hygroscopic. The density, the effective density also provides some information. Initially the density is characteristic of organic aerosols, but once this haze evolved and it become more representative of a mixture of organics and inorganic sulfate, ammonia, and etc. So why haze develops so rapidly? The growth is so rapidly, and that is primarily attributed to the very high concentration of gas species. In Beijing, the SO2 concentration can easily be over 10, 30 ppb, and very high NOx concentrations. And in some cases, we saw those two episodes I show has very high ozone concentration, indicating that photochemistry is very important. And also we see a lot of traffic emissions, benzenes, toluene, and particularly xylene and toluene. And those are compounds. So those gas species are mainly the driving forces for the very efficient aerosol growth processes. And just for a comparison, I mean, how the aerosol compositions look at in different urban cities. So here I got several places in Texas, and I got Los Angeles, and Beijing is here, and Mexico City is here. Then those are the average mass concentrations. Of course, Beijing is very polluted here. One thing I do like, so you see some differences, but overall you can see the organics is a big contributor of those in the pie chart. And the other thing I do like to mention is that if you compare these two locations, and the chemical composition in these two places, Beijing versus Los Angeles, is almost identical. And this basically tells me that those are basically the chemical composition characteristic of urban particles. And we talk a little bit about the Los Angeles haze, and the area used to be very polluted. I think it's getting better now, and you're still hazy. But area has gone through a very long pathways in terms of improving air qualities, and those are historic trend of some compound, NOx, ozone has been, and those concentrations have been reduced significantly. And so I think Beijing probably is right now is here, and they probably have to go through the same route, I mean, in order to achieve better air quality. So Los Angeles basically is probably is a better case for most of the developing countries to study. So now I'm going to emphasize on some challenging issues concerning aerosol nucleation and the growth. Aerosol nucleation really is a very complicated problem. So you can look into two complementary. So if you look into so this aerosol nucleation basically involves phase transformation from vapor, and our case is either to liquid or solid. And so there are several fundamental principles. First law, and you have decreased enthalpy when you go in this direction. Second law, of course, you also decrease entropy. And if you look into the free energy in negative term, and then there's a positive term, so you may end up with a free energy barrier. And by the way, those are being discussed in a previous review for chemical review articles. So if you have a single component thermodynamic system need to be super saturated, and then you run into this maximum, the nucleation barrier here, and you can actually calculate this using the Kelvin equation, and you derive this equation here. And this basically tells you is that if the particle size is very small, there's a tremendous supersaturation required. So nucleation essentially include two fundamental barriers. So one is the free energy barrier, and the other is the Kelvin barrier. So, so particularly when we're looking at phase transformation from vapor to liquid or solid, and you would think once you overcome the free energy barrier, I mean, the growth is going to be spontaneous, but in reality, you have to consider the Kelvin phenomena. So that's one of the biggest challenges here. So what are the chemical compounds that can help you to overcome the free energy barrier? And what are the compounds that's going to help you to overcome the Kelvin barrier? And so over the last few years, people have been looking into the different compounds that may do this, may help you to do this. And here I'd like to mention one of the latest interests is actually to look into the potential contribution of organic species to aerosol nucleation process here. So we published this article in 2004. So what we're looking at here is we measure nucleation rate up to use a nano-DMA, And if you only have sulfuric acid, water, that's the nucleation size distribution you measure. And if you add this organic acid here, and at lower concentration, higher concentration. So our study shows that the organic acid may actually help you to nucleate particles. And the reason for that is because they form very strong hydrogen bonding complexes. And you probably cannot see here. So this is a quantum chemical calculation. That's a molecular dynamic calculation. I'm almost done, right? And this is some studies we did here. And recently, there have been studies from the cloud chamber, and they also recognize the contribution of oxidized organics to aerosol nucleation, and also I think there's just a paper article published in Science last week. They look into the covalently bound formic iso2 complex anhydrate, and that may have an implication in aerosol nucleation. So now I'd like to talk a little bit about the growth process. So traditionally, people think the organic aerosol growth can involve partition and also can involve aqueous phase reactions. So when you have VOCs oxidation taking place in the atmosphere, and so one of the consequences is that the volatility of the compound may be decreased. So you go from highly volatile, intermediate volatile to extremely low volatile compounds. But alternatively, so some of the intermediate volatile compounds, semi-volatile compounds, they may not necessarily condense, may also engage in aqueous phase reactions. One point I would like to mention here is that if isolate secondary aerosol grows through this route versus this route, and you may have different reaction product, and they may lead to different hygroscopicity, and also potentially different optical properties. And the other thing I do like to mention is the partition process is proportional to the first power, and this ideally may, because this may involve several of those, so this may at least involve second power. So this may actually happen very efficiently when the concentration is lower, and this may actually occur very efficiently when the concentration is higher. So that may actually explain some differences between Beijing and some developed countries. We actually look into some of those reactions exposing nanoparticles. We see those like a glycol actually make the particle grow, and those are basically hydration reactions. And here are some thoughts I put out here in terms of understanding aerosol nucleation and growth. And of course, I like to, I would like to engage in more discussions with you guys about some of those issues. And finally, thanks for your attention.
Thank you.